Okay, so here we go. So last time we were talking about, I keep saying last time. Last time we had an exam. Last week with our last lecture, we talked about what to do about this new situation we're entertaining of, what if you want to do a chop it up, add it up, a whole is the sum of the parts, but what if your domain is dimensionally weird, right? So like a one-dimensional thing in a two-dimensional world, something like that. And so we argued that you can still chop it up into little pieces, and on each little piece you can still kind of multiply something per unit size times size, and it's just adapted appropriately to the circumstance. We talked about this notation, this terminology. We talked about this strategy for how to compute. Namely, we're basically copying off of the old idea of change of variables, just that now it's a parameterization that we are pulling back through. And blah, 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 stretching factor, et cetera, et cetera. We talked about all that last week as well. Here was our formula for how to compute that scalar line integral. Okay, so we did some examples. I won't repeat. Where we ended last time was entertaining this seemingly same situation of what if I want to chop it up, add it up, but on on a curve, just like before. But what if the thing that I'm interested in computing is work? And what we found is that it doesn't really quite fit our previous construction. In particular, we found that it matters which way we go. We can't just talk about a curve. We have to talk about an oriented curve in order to be able to talk about, in particular, the displacement. What is our displacement if we don't know which direction we're going? Right? So that direction matters. And then also we found, and this is about where we left off last time, that not only is the differential a vector, not a scalar, but furthermore our integrand is a vector, not a scalar, and the multiplication, well, that's a dot product, which is a vector multiplication, not a regular old plain old scalar multiplication. This is a different construction. It's very closely related to the scalar line integral construction, but it is importantly different. So we call this a vector line integral. Okay. So now how to compute. I think this is about where we left off last time. Recall all of this from our previous discussion of scalar line integrals. And in fact, notice that everything we need is already right here in the picture. So, in particular, this dx vector. That, in the scalar line integral context, we were interested in it because its magnitude was the ds that we were interested in. Now, we're not really particularly interested in ds. We're interested in the dx vector itself, which I already know is both of these things, which, when I plug into my vector line integral formula, gives me these two alternative notations, alternative formulas, whatever you want to call them, for vector line integrals. And mostly to the point is notice that this one here is a pullback through the parameterization. Everything's in terms of t, and so this is a plug and chug opportunity for us. Okay, let me hit the pause button right here. How are we doing? Everybody with me? All right, so let's do one. We are going to compute the amount of work that it takes, right, to do a certain task. We have a given force. We have a given curve. The curve is counterclockwise along the top half of the unit circle. So again, we have an oriented curve. We have a force vector field, and we're basically going to plug and chug into the formula. Now there is one little awkward physics aside that we have to talk about, and it's annoying. This is what I like to call the equal and opposite situation. Let's look at this pen that I have in my hand. Not falling, right? And that's not because there's no forces acting on the pen. In fact, there are two forces acting on the pen. Gravity's pulling down. I am pushing up. And these are, equal and opposite, they say. otherwise known as negatives of each other. And because they are negatives of each other, they add up to zero, and zero force means zero acceleration, which is why it doesn't fall. Okay, so point being, when you have a situation where there is a force being applied, you have to ask yourself the question, is the force that I was given the force that I am applying, or is it the force that's being applied to me? Right? And the difference matters because, the one's the negative of the other, so which one's the right one? So what you have to keep in mind is that if we're interested in the amount of work that you have to perform, then we are interested in the force that you are pushing with. And this is not the same as the force that the wind is applying to you. The wind is applying F to you. That means the force that you are applying to oppose the wind is the negative of that. Right? So, because we're interested in your work, we need to know what your force is, and your force is the negative. Right? Make sure not to forget that negative. It's the negative of this given thing called F, that is the force that the wind exerts on you. How we doing? Everybody with me? Okay, it's an awkward, annoying little detail that we always tragically have to think about, depending on how the question is phrased. It's all a matter of interpreting the phrasing, right? But you always have to think about it when you're doing a word calculation. Okay. All right. So, in this circumstance, integral of negative f dot dx. Fine. Now the plug and chug part. Excuse me. Lucky break. Counterclockwise, top half of the unit circle, easy to parameterize. We've done that parameterization many times in the past, and so one of our most familiar parameterizations, and I'm deliberately starting with an easy one so we can get one into the win column before we look at harder situations. Cosine sine, right, goes counterclockwise around the unit circle. Okay. We are interested, of course, only in the top half, and as such, we are interested in only these values of t. Okay. So we take the derivative. Easy calculus there. We plug into our formula for how to compute a line integral. Right there. Right, dx is x prime dt. And it's really just a matter of plugging it all in at this point. Let's see here. So x prime is this, as we noted previously up here. Our vector field F that was given, let's see, where is that? Our vector field F, y comma negative x, right there. Now, a common mistake a lot of students make is they double count this minus sign by, on the one hand, having the minus sign in there, as they should, but then misinterpreting the F as, wait a second, which force is it that I want to, do I want the force acting on me, or the force that I'm acting on it, etc., and then they throw in an extra minus sign. And you've already done that. We already have that minus sign. That's this minus sign. What I have in green here is pure recopy, right? The equal and opposite has already been accounted for. So don't accidentally double count that minus. This leaves us with our usual question of, what do I do with x and y? How do I know how to plug in for x and y? Answer, this is the formula that you are pulling back through. In this case, it's our parameterization that we're pulling back through. And notice right here are the formulas. And it says right here, x is cosine t. So that x equals cosine t just goes, x cosine t right there. And don't forget that we likewise have y equals sine t. And so right there. What do you think? Is everybody with me? All makes sense. Okay. And as I said, it's all plug and chug at this point. This is a single variable integral. You got to write down the dot product, blah, 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 Pythagorean identity, but it's basically straight plug and chug to an answer there. Okay, so vector line integrals. I think one of the funny things about vector line integrals versus scalar line integrals is even though vector line integrals are the more sophisticated concept, they're arguably easier to compute because you don't have to find ds. You don't have to think about the speed. Speed, after all, is a square root. Square roots can be really inconvenient. Now, we had some lucky examples that we saw previously that didn't really come up. But don't expect any square roots to come here because you don't have to take the magnitude of the x prime vector. So weirdly, the more sophisticated construction is actually easier to crank out in practice most of the time. Okay, all right. Now, you would think that you should get the same value no matter what your parameterization is. After all, that was the case for scalar line integrals. One of the first observations we made, labeled it a handy fact, right after we wrote down the pullback formula for scalar line integrals. This being a very similar construction, you'd think it'd be the same. There is a key difference, though, and that is you have to have the correct orientation. Right? If you parameterize backwards when you're doing a vector line integral, you will be wrong by a minus sign because, well, every dx that should be going this way, yours will be going the opposite direction. So every term in the summation will be off by a minus sign, therefore your answer off by a minus sign. So this is kind of a sort of a good news / heads up. The good news is it's largely independent of orientation. It's independent of parameterization. Just do keep in mind that you have to parameterize the right direction. Another way to say this, it does not matter how you parameterize the oriented curve. But you do have to parameterize the correct oriented curve. If you orient the wrong way, you've correctly parameterized the wrong oriented curve. So heads up on that, do be careful. Now, here's another way to say it. Same statement, different twist, and a little bit of notation and some formalities. Let's label with a superscript of a minus sign what we mean by going the opposite orientation. So if I have a curve C that goes from A to B, then C minus, same underlying curve, just going backwards from B to A. That minus will give you the negative of the correct of the previous answer. So the twist I'm going to put on this, and the different take I'm going to propose here, is it's not exactly that you have to parameterize the correct direction. You just have to be aware that if you parameterize backwards, your answer's off by a minus sign. And the thing is, sometimes that's okay. Sometimes it's easier to parameterize the wrong way, and then just say, oh yeah, and by the way, I'm parameterizing backwards, so I'm going to, fair is fair, I'm going to accommodate for that by putting in a minus sign, and then it's fine. And everything's good. Perfectly respectable way to go. Okay, let me show you some examples. Now this is, I'm actually going to show you 3 different solutions to this example here. Same as the previous, so top half of the unit circle, blah, 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 vector field forces, blah, blah. The only difference, now we're going to go clockwise instead of counterclockwise. How does that change things? So I'm going to give you 3 different solutions to this problem. And then I'm going to kind of disallow a 4th, but let's not get ahead of ourselves. So for the first 2 solutions, we just have to figure out how to parameterize clockwise. And I'm going to show you 2 different ways to do it. Here's the idea. If I parameterize clockwise like that, I propose that this angle right here is my parameter. After all, if I'm going clockwise as indicated, here's where t is equal to 0. Here's t increasing. right? And here's t equals to pi, and all of that tracks with that being my my interpretation, my labeling of the angle t. Okay, then I make the observation that if that's t, then that's pi minus t. And the good thing about knowing that angle pi minus t is that this is otherwise known as theta. That's the good old familiar polar coordinate theta, and it's easy to talk about the location of a point. Let's see here. Here we go. The location of a point on the unit circle. When I know theta, no problem. Cosine and sine of theta. But specifically, it does have to be theta here that I take cosine and sine of. If you say cosine and sine of t, that's not correct. T is the wrong angle. T is this angle over here. It's the natural way to parameterize, but it's not the polar coordinate theta. So theta's there. How are we doing? Yes?
If you're parameterizing it on like a sort of regular curve that doesn't have any trig functions,
Yeah.
how do you tell which way is like left to right or right to left?
There can be a problem of how to figure out which direction have you in fact parameterized. A good easy way to do it is to take the derivative and just look at what direction does that derivative vector point, right? So the derivative vector will always be a tangent vector to the curve, and it'll point. I mean, you have to look at the picture and think about your geometric intuition, but it should point in the correct direction along the curve. Does that make sense?
Yeah.
Yeah. How do you go from cosine of pi minus t to negative cosine?
Yeah, that's very great question. That was my next thing. So he asks, how did I get from here to here? And there's a couple different ways that you can think about that. One is to recall all of the old symmetry formulas from your high school trig class. This is one of those symmetries. Another way to do it is to recall the angle addition formulas from high school trig class, which I understand that a lot of high schools have kind of undersold, at least as I see it. So what I'm going to say about all of that is it's unfortunate that a lot of high schools have made this, I think, imprudent decision to undersell a lot of that stuff, right? So symmetries of trig functions, important. Angle addition formulas, important. They're unavoidably important in a lot of situations, especially for those of you going into engineering or physics. But certainly for Math 219, I do need students to brush up on all of that old high school trig stuff. So make sure you're good with the symmetries of trig functions, sine and cosine. I mean, the others you can think through as needed. But make sure you're good with the symmetries of sine and cosine functions and the angle addition formulas for sine and cosine. Is that cool? Yeah. All right. Okay, yeah, so whichever of those points of view you prefer, and there's your parameterization. Now, let me show you a different approach. How to parameterize this curve. Again, keep in mind, we want to parameterize clockwise. So I want to go that way, or let me be a little bit more compact here. I want to parameterize like that. So I'm looking for an XY that gives me that blue orientation on the curve. And here's the clever idea here. Notice that the reflection of that blue curve, pretty easy to write down, the reflection of the blue curve is counterclockwise along the unit circle, which is our old friend, cosine comma sine. Right? Easy case to make in this case. You just notice that there's an easy reflection over the y-axis. And so, okay, well, I know what this green parameterization is. I know what this reflection does. I can just see from the picture that this reflection is just going to put a minus sign on the x-coordinate. And boom, there's my parameterization. And notice that it gives me, in fact, the exact same result. I get the same final parameterization either way. How we doing? Everybody's all right? Okay. So I advise that you be comfortable with both of these approaches on an exam, if it should be the case, or homework question, whatever, right? In any circumstance that you need to use one or the other of these, if they both work and make sense in that other context. I mean, it won't be exactly this, of course, right? But if you have the choice, then yeah, sure, you're free to choose whichever one of these you like better. But just do keep in mind, sometimes, the problem will be different, and there might be an opportunity to use this reflection idea. But that idea over there, just the different question, it just doesn't fit, and it just doesn't really work as well, and vice versa. So I think it's important to be good with both of these strategies, as they will apply in different circumstances. Okay. All right, and once you have your parameterization, plug and chug as before. So that's 2 solutions to this revised example. The third solution, and in this case by far the best solution, is to say, this is exactly the same question as we already know the answer to, except we're going the opposite direction. That's the only difference, is that we're going the opposite direction. And opposite directions just give us a minus sign. We already know what happens, what the answer is for going the for going the counterclockwise direction. We already know the answer is pi, and so minus pi. So again, sometimes, even though arguably I kind of, I'm making reference to an integral that we computed where I parameterized the wrong way. But I've accounted for that by recognizing that the curve I actually want is oriented oppositely, that gives rise to this minus, and this is a perfectly fine solution. How we doing? Everybody all right? Okay. Okay, moving along. So now we're going to entertain a different question. Let me remind y'all, I'm going to go back all the way up to here. Where all of this vector line integral stuff came from was we were asking a question about work. Right? All of this discussion has been in the context of work. And in order to make sense out of computing work, I had to have my vector field represent a force. Said differently, if I am looking at a vector line integral like this, looking at a vector line integral, if the vector field represents forces, then I know how to interpret this expression. When I'm talking about forces, this expression means work. What if I'm not talking about forces, though? Right? What if, and keep in mind, we certainly have this situation, what if my vector field is not representing force? What if my vector field now represents the velocity of a flowing fluid? And representing a velocity of a flowing fluid, now what does this line integral represent? What is that? It's not work, right? I mean, this is only work if the integrand is force, which it isn't anymore. Now it's just it's a velocity. It's a totally different physical concept. So, big question of what is the vector line integral in this case? Okay, well, there's an answer to this question. Couple of bad things about the answer. One bad thing about the answer, it's not a pre-existing physical concept that you've previously seen, more than likely. Right? So I'm not going to be able to take the expression as given and sort of interpret and, bam, it's that old concept from high school physics. It's not. It's a weird thing. It's sort of a new physical concept. And so it doesn't lend well to starting with this expression and then going down and trying to make sense out of it. What I'm going to do instead is I'm going to ask a new physics question. It's going to be an unfamiliar physics question. It's going to seem a little strange. Why would I be interested in this thing? And bear with me. The reason we're going to be interested in this new weird physics question I'm going to propose is because the answer happens to be morally this asterisk. There's a little detail we'll have to talk about. But the weird question I'm about to ask will lead to an interpretation of vector line integrals in the fluid flow context. So, bear with me. Again, it's going to seem like we're going to be doing some weird things here real quick. Now, all of this is just a recopy, mostly for student convenience. If you need a quick reminder as we do the calculation on the next page, remember this is our setup and relationship between the objects in play that we're about to talk about. Okay, here we go. Here's the question. I told you it was going to be weird. So suppose we have ourselves a curve, and suppose I take some area perpendicular to the curve, and imagine kind of dragging that along the curve to create this, I like to think of this as kind of a tube, if you will. Kind of a tube surrounding the curve there. Right? So the idea being that as I move along the curve, if I take a cross-section of the tube, the cross-section of the tube is always this same area. Let's just say. So, well, there's a certain amount of fluid in that tube. If, again, I keep in mind, we're considering the context where we've got a flowing fluid. That's what our vector field represents. So there's a certain amount of fluid in that tube. To some extent, that fluid will be flowing along the curve. And to some extent, that fluid will be flowing perpendicular to the curve. And I want to get a handle in some sense for the total, whatever that means, the total rate that the fluid is flowing along the curve. It's kind of a weird thing to ask. Again, I recognize that is weird. Okay. Well, here's the idea. If I want to know the total amount the fluid is flowing along the curve, I'm just going to look at each little piece of fluid. There's a little slice of my tube, a little slice of fluid. It's easy to write down what the volume of that is. Right? This volume here is just the cross-sectional area times the thickness ds. So, easy formula for how much fluid I have in that little piece. Next, I want to know the extent to which the fluid is flowing along the curve. Now, mind you, that's not the same as the actual flow. This fluid might actually be going in this blue direction down here. And if the fluid is going in this blue direction, well, to some extent, this blue velocity is not along the curve, right? But I can talk about its component. The component along the curve, the component in the direction of that unit tangent vector t. Reminder, the unit tangent vector t always goes along the curve. And I know how to compute components. Components are computed with dot product with the unit tangent vector, in this case t. So all together, here we go. For this little piece, if I want to know to what extent is this little piece of fluid flowing along the curve, there it is. That's how much fluid, that's how much it's flowing along the curve, and that's a corresponding little piece of this weird question that I'm trying to find the answer to. So all together then, if I add up over the entire curve, so again, if I, add this up for not just the one little piece ds, but the entire curve all together, do an integral along the whole curve, in other words, and plug stuff in and factor out constants, etc. Right, so all of this is dq. Notice the area is a constant, so it factors out. And here's the lovely result. This thing, this weird concept that I asked about for no apparent reason other than maybe you trust me, right? This weird thing, very closely connected to line integrals. And because you can see it right here. There's the line integral. And again, asterisk, the quantity in question is not just the line integral. There's also the business about this cross-sectional area. So, all right, the way I'm going to deal with that is just to say, well, I like this area here, I can think of dividing over to the other side of the equation, and then I can just say, okay, per unit cross-sectional area, Obviously, if you have bigger areas, then you're going to have more fluid, and that leads to a bigger quantity. Sure, of course. So per cross-sectional area, the vector line integral represents how much the fluid is flowing along the curve in the sense that we analyzed in this question. So I think that's a nice, it's a new physics concept. This isn't something you've probably seen before. It doesn't come up in high school physics classes that I'm aware of. It's kind of a weird, it involves some pretty sophisticated stuff here, right? But this gives a nice fluid context interpretation of a vector line integral. When you're looking at a vector line integral of a fluid flow, the line integral represents, in some sense, how much the fluid's flowing along the curve. Pausing for questions. How are we doing? All right. It doesn't roll off the tongue as nicely as work. Right? If you're talking about forces, line integrals are work. Nice and easy. Here, it's you kind of have to wave some hands a little bit. Okay. So here is a special case that gets discussed a lot. This is an important special case. In other words, you may at some point be taking a line integral on a curve that is a closed curve. A closed curve just means that it starts and ends at the same point. In other words, that it loops back around on itself, such as, for example, this curve here. Let's say we start there, it goes around, and it comes back and ends right where it started. This is what we call a closed curve. In the case that you're talking about a closed curve, we give a special name to the vector line integral. And the special name that we give to it is circulation. We use the lowercase Greek letter sigma because of the what do you call it? Is that alliteration? Sigma starts with the same sound as circulation. Anyway. Okay. So why do we call this circulation? Well, I think there's a pretty good motivation for it. After all, let's not forget, the curve makes a loop of sorts. I'm going to loosely say that the curve kind of goes around in a circle of sorts. And don't forget that the line integral, what the line integral represents, it represents the extent to which the fluid is following along with the curve. Right? So to what extent is the fluid doing what the curve did? Said differently, to what extent does the fluid loop around itself just like the curve did? In other words, to what extent is the fluid kind of going around in little circles? Kind of, sort of, again, if you will. So, thus the term circulation, I think is pretty natural if you think about it from this point of view. Is everybody all right with that? Okay. All right, so why do we need circulation? A couple different interpretations I'm going to give you. One is, I like to think of the fluid as being a physical fluid, like water is an easy one to think about. And so let's suppose I have water, and the water is, would make a little whirlpool kind of thing here. There's our vector field, in this case, kind of a whirlpool. What would happen, would you think, if you were to take, a leaf, dead leaf, as falls into little rivers during the fall season routinely, right? If a little dead leaf falls into the surface of a river and it falls right onto where the fluid is going around in circles, what does the leaf do? Well, the leaf will start spinning. Right? And you don't even have to drop the leaf right onto a little whirlpool. You can drop a leaf or any other small, low mass, floating thing. What happens if you drop it into the river? Well, it's going to go downstream, but it also might turn as it floats down the river, as it floats downstream. And I propose that circulation is a way to get your hands on, in some sense, on which direction and how much is this dead leaf, let's say, go back to this metaphor, how much is it going to be rotating? And I'll point out that if the water is flowing along the sort of the edge of the leaf, wouldn't you imagine that the leaf would start rotating that same way? Right? And so I would propose in this circumstance here, and keep in mind our curve, right? Our closed curve is going around that way. To what extent is this leaf going to be rotating around, as indicated by the boundary curve? To what extent, in other words, is the water circulating around the boundary of that dead leaf? And, well, in this case, it looks like a positive amount, right? The water is moving around the boundary of this leaf to a positive degree. And so we have a positive circulation, meaning that we would have a positive rotation of the leaf in that counterclockwise direction. That's just a way to think about it. A way to think about circulation. Likewise, now let's ask the same question. Same little whirlpool of water here. Right? But what if I were to ask the question backwards? What if I were to ask, to what extent is this leaf rotating clockwise? And I would answer by saying, well, it's not rotating clockwise, it's rotating counterclockwise. Look at the whirlpool. The whirlpool, it's the same whirlpool. Just because I phrased the question backwards doesn't change the fact that the whirlpool is still going around counterclockwise. So another way to say it is, to what extent is the leaf going to be rotating clockwise? Well, a negative amount clockwise, because it's going counterclockwise. Right? So this is what it would look like for circulation to be negative. Negative circulation just means that the actual flow of the fluid is opposite of the direction of the curve that you computed the circulation. Everybody all right? Okay. And one last example. I mean, just in recognition of the fact that both of these examples were kind of perfect, like the water is going around in perfect circles, centered on exactly the center of the leaf. This is kind of the most ideal sort of a picture, and I want to recognize it doesn't always look like that. I mean, this is a more realistic scenario here. What's happening to this leaf? We could reasonably ask as it rotates, subject to the forces by the water. Well, this is awkward because some pieces of this of the water flow, like for example along in here, the water flow is that way, which is pushing along that edge. It's pushing the leaf clockwise, whereas over here on that side, the water is pushing on the leaf counterclockwise. So here we have kind of a competing forces sort of a thing. I mean, in some sense, it's there's going to be a tug of war between the two different sides that the water is pushing on, and we'd have to actually compute the integral to see for sure whether this outside force pushing it counterclockwise was more or less than the inside force pushing it clockwise. And so that's why I leave the answer here as question mark, because it's really not obvious from the picture. Does that make sense to everybody? Okay. All right. Okay, one last thing I want to say about circulations is just a more sort of persuasively relevant example. One could make the case that, I don't believe I need multivariable calculus to understand leaves floating down the river. Who cares, right? Who cares at all about leaves floating down a river? So here's a more relevant example. And I guess I will go ahead and draw a little picture. Ooh, let's see here. I've got some space up here. This is about airplanes. How do airplanes work? Well, it's tricky, in fact. And here is an airplane wing. something like that maybe. Cross section of an airplane wing, right? I don't know if y'all have ever taken a close look at airplane wings, but they're not just flat. They have a very special shape to them. And the reason they have that special shape is because of how to use physics to make certain facts of physics, the Bernoulli effect, in particular, to make the airplane actually fly, right? Key fact. So let's talk about lift. And it turns out that when you have a fluid, in this case air, flowing over a surface, that creates lift. That creates a force in that direction. But here's the problem. The air is also flowing underneath the wing. Right? And that creates a force in that direction. So the goal in finding an ideal shape to make an airplane wing is to shape it such that, and again, I'm leaving out a lot of physics here because it's not, this is not an engineering class and there's a lot of details, and that's, y'all can deal with that at another time. But we want to make the upward force, the lift, right, to be greater than the downward force, the I don't know, pull down, whatever you call it. We want, in other words, the sum of these orange vectors to be up. All right. Well, another way to think of this downward arrow is that instead of thinking of my curve like that and like this, top curve and bottom curve, I can recognize that I want to subtract this amount, or, think about the upward lift instead of the downward by turning the curve around the other direction. And so, in fact, what we find ourselves doing then, if we want to compute the total net lift of an airplane wing, what we're doing is we're doing an integral around this closed dark blue curve. Specifically, it's going to be a particular integral that involves the vector field of the flow of the air. And so that vector line integral around the boundary of the cross-section of the airplane wing will compute lift. So very specifically, it is a vector line integral that computes that lift. So, big deal, right? Airplanes are a massive, huge application of engineering, and ultimately, it's this construction, a vector line integral, that's essential to making that all work. Everybody buy it? It's kind of a cool, application to have in mind. Okay. Alrighty then. Moving along. So here's a quick example. Another example. Sometimes you get lucky. Y'all know that I'm a big fan of shortcuts when they present themselves. The big one that I've presented so far is symmetry. Right? I claim ballpark. Again, I don't have the data, but just based on my memory, I think about 20% of the integrals that I saw in my undergraduate physics major were zero by symmetry. Another very significant fraction, I couldn't tell you what, maybe 10%? A very significant fraction, though. There was what I'm loosely calling fortunate geometry, or geometric lucky breaks. And this is a really nice time saver when these circumstances arise. So I do want you to be on the lookout for this kind of thing. Don't just always be into plug and chug mode when it comes to computing vector line integrals. So in particular, let's think about the following. We have a curve here. It's parametrized in a weird way. This curve is parametrized where instead of giving you x, y, and z as functions of time, here I'm giving you rho, phi, and theta as functions of time. from which you can plug into the usual spherical coordinate formulas. In other words, you can sines and cosines and stuff of these angles and get a rectangular parameterization of this curve. And you can imagine what's going to happen when you take the various sines and cosines of these things and multiply as you must. You get a very ugly parameterization of this purple curve. Everybody with me? Everybody see how that's scary looking, and we don't really want to have to deal with that if we don't have to. Okay. Now let's look at the vector field. The vector field we're given, here it is. There's the formula. And notice it is always a scalar multiple of the position vector x. And there's something really valuable to notice about the position vector. Notice that my curve has rho equals 1 everywhere. That means that my curve is always along this unit sphere. That means that my position vector is always on this unit sphere, and spheres have wonderful geometry. In particular, a position vector, sphere centered at the origin. Position vector is always perpendicular to the surface. This is a unique feature of spheres centered at the origin. The position vector is always perpendicular to the surface itself. So, altogether then, notice that my curve and therefore my dx vector, wrong color. My curve and therefore my dx vector always parallel to the surface. Whoa. Okay, that was not my fault. I don't know why this thing just switched like that. Oh, nope, now it's not letting me switch back. Come on. There we go. There we go. Okay. Fingers crossed it doesn't fit. Okay, repeating myself. So the dx vector is parallel to the surface of the sphere. But notice that my vector field is always orthogonal to the sphere. And that means that these two vectors, f and dx, are always perpendicular to each other. That means that this dot product is equal to 0. That means that my integral is equal to 0. Didn't have to do any nasty trig from this parameterization or compute an antiderivative for the integral or nothing. Just dot product is 0. Integral is equal to 0. Everybody see how that happened? So we got lucky with the geometry. Again, this is not rare. This specific example, admittedly, very manufactured, of course, right? But the world is full of spheres. And the world is full of radial vector fields. This is actually a pretty common scenario. And therefore something to be very much on the lookout for. All right, is everybody good? By the way, you'll notice I'm not giving away any free information here, but if you look through my old exams, you'll find there's a bunch of these on there. Right, so good trick to be on the lookout for. Okay. All right, the last thing I'm going to do for today, in the remaining minute and a half, we'll just kind of start on this next bit. It's not that big a deal. Here's our old formula for the dx vector. Dx is x prime dt. We left it at that. Let me just point out, though, that x prime, I can just write that down in coordinates. So I didn't really do anything significant there. Just wrote it out in terms of coordinates. And now let me again not do anything particularly significant. Let me just kind of distribute the dt. Right, why not? We haven't done this yet for no particular reason, but let's go ahead and just distribute that dt. And then I'm going to point out that, x prime dt, very naturally we would call that dx. Likewise, y prime dt, we would call dy, et cetera, et cetera. So, with this in mind, that you can rewrite the dx vector as dx, dy, dz, you can plug that in to your vector line integral formula. The vector field itself is going to have coordinates, and it doesn't really matter, but arbitrarily it's fairly common to call those coordinates P, Q, and R. Whatever. You can call them F1, F2, F3 if you like. And this gives us an alternative notation for a vector line integral. The vector line integral that up to now we've written as f dot dx, we could alternatively write it as pqr dot dx dy dz, and you can just multiply out that dot product and rewrite it therefore as this: pdx plus qdy plus rdz. And there are some things to say about this alternative notation for vector line integrals, and I'll say those things next time. So I hope you all have a good rest of your Monday. Thanks for coming. See you Wednesday. Let's see, where's